Welcome back to TED Talks. We are going to have a session of a continuation of calculation of empirical and molecular formula. Earlier on we had seen how to go about with the calculation of empirical and molecular formula. But as we proceed, let us try to see numbers that may try to give us some little bit of headache. So we are going to continue with the continuation of the calculation of empirical and molecular formulae of compounds. So let us try to look at another number here. Let us again use a hydrocarbon. A hydrocarbon W consists of 82.76% carbon and the rest being hydrogen. The first part of it says calculate the simplest formula of W. Then the next part says if the vapor density of the hydrocarbon is 29, determine its molecular formula. Given that carbon is equal to 12 and hydrogen is equal to 1, let us look at how we can determine the empirical and the molecular formula of this hydrocarbon with the percentage composition by mass of carbon being 82.76, and then they say that the rest is hydrogen. Even if we have not been told that the rest is for hydrogen, we just know that a hydrocarbon consists of carbon and hydrogen atoms only. So since they have said that the rest is hydrogen, let us firstly start by getting the percentage composition of hydrogen. The percentage composition of hydrogen will be 100 minus 82.76, and this one will give us, let us use our calculator, 100 minus 82.76 this one gives us 17.24%. This is the percentage of hydrogen in this hydrocarbon, W. Now let us go ahead and calculate the empirical formula using the steps that we have seen before. So we start with the component elements. In this hydrocarbon we have carbon and we have hydrogen. The symbols of the elements are written in the same row side by side, but I say there must be some fair distance between the two chemical symbols, so that in case you get a long decimal number, it should not come up to down here. It should not conflict with the space for the values that should be under hydrogen in this case. The next thing is we need to write the percentage composition of each. So for carbon it is 82.76, for hydrogen is 17.24. Then let us also remind ourselves by putting down the relative atomic mass of each element. For carbon it is 12 and that of hydrogen is 1. Next easy, we are going to get the number of moles, and we are done, as we have done before, by dividing the percentage composition of each element by its relative atomic mass. So in this case for carbon is 82.76, we divide by 12. Hydrogen is 17.24, we divide by 1. What we get is the number of moles of each element in this compound. So let us look at that of hydrogen. That of carbon is 82.76. We divide by 12. Oh, it has given us 6.8966666667, and this one gives us 17.24. Please, I say that we need not in any way round off. Leave the values as you have seen from the monitor or from the screen of your calculator. Next is we are now going to the mole ratio. The mole ratio. So the mole ratio is got by dividing the two number of moles by the smaller number of moles. If there were 3, we would divide all through by the smallest number of moles. So here we are going to divide by the smaller number of moles. So it is 6.89666667. We divide it by itself by 6.89666667. Even here, the 17.24, we divide it by the smaller number of moles, that is 6.89666667. What we get from here will be our mole ratio. So our mole ratio will be a ratio of 1 to, let us get the other one also. So it is 17.24, we divide by that. And here we have got 2.499758337. Now we have an issue here. We have reached a point whereby our mole ratio is having a whole number and then a decimal number. At this point, you can now round off to one decimal place. That is if and only if we have got the mole ratio. At this point, when you have just got the number of moles, please do not in any way round off the number of moles. Leave them the way they are. But when it comes to the mole ratio, please, when you have got a ratio of 1 to some decimal number, first round off to one decimal place, and in this case it becomes an approximate value. It is approximately 1 to 2.5. Now, the point is here. In most cases, we look for a number which we can multiply each number of moles with in order to get a whole number. But the simplest way is here. What we are going to do is, we shall have to convert this decimal number into a fraction. As you can see, we are having 2.5 as being our fraction. So we shall get the fraction which corresponds to 2.5 this way. Firstly, start with the lowest term of this decimal value here. The lowest term of the decimal value 0.5 is 0.5. Then from 0.5 we go stepwise, we go to 1.5. Then later on we shall reach 2.5. We shall get 2.5, a fraction which corresponds to 2.5, but progressively. So what gives us 0.5 in this case is a half. For me to get 1.5, which is the next value after 0.5, I'm going to add the denominator to the numerator and then maintain the denominator. So it will be 2 plus 1, giving us a total of 3 over 2. We maintain the denominator. Please try to enter this in your calculator. You're going to get exactly 1.5. Here, this one here, it is 2 plus 3, which is 5 over 2. So this is how we can get a fraction which corresponds to 2.5. Now we shall carry that fraction and bring it back here. So we have approximately a ratio of 1 to 5 over 2. Now what you do next is multiply both sides by the denominator. So we shall multiply this one here by 2 and this one also by 2. What we get from here gives us now the real mole ratio which we are going to use, or from which we are going to get the empirical formula. So this one becomes a ratio of 2 to 5, meaning that the empirical formula is C2H5. And we can therefore conclude that the empirical formula is C2H5. I want to take it through something small again. In case it is a 0.3, let us say, supposing we had a ratio of 1 to, say, let me use 1.299375154. If this was our ratio, still we are going to convert this one here into a fraction, but by firstly, if this one is our mole ratio, we shall firstly round off to 1 decimal place. This one becomes 1.3. Now, if it is a 0.3, make sure that you get a fraction which corresponds to the 0.3, but make it be a recurring decimal. It will give you a very good fraction which you can use the way we have used this one here. So, let us try to see from here. Let's try to work it out from here. So, if we want 0.3, if we want 1.3, we start from 0.3. but will be recurring, then we go to 1.3. So 0.3, a fraction which gives us 0.3 recurring is a third, 1 over 3. Then this one here becomes 3 plus 1, which is 4 over 3. Then we bring it back here. It will be approximately 1 to 4 over 3. Then multiply both sides by the denominator. So by 3. And it will be approximately a ratio of 3 to 4. And then your empirical formula will be this element here, 3, then this element here, 4. That is how we can get a decimal number. Please, if you don't round off from here, then you are going to get a very good value down here, which when rounded off to the say to 1 decimal place, you can easily get a value which will be either a 0.5 or a 0.3, or it can be a whole number straight. So don't make a mistake of rounding off your number, or your number of moles in this case. Don't round it off, leave it the way it is. Use it until when you reach the mole ratio, when you have got it, then you can round off to 1 decimal place, and then you get a fraction which corresponds to that very value, multiply both sides by the denominator and get the, in this case you get the correct mole ratio. So that is how we can get it. And that was part A. We have got the simplest formula of the compound, and then the simplest formula is C2H8. Next is, they are saying we should calculate the molecular formula if the vapor density of the hydrocarbon is 29. So let me use this downer part here for calculating, in this case, the molecular formula of this hydrocarbon W. I believe that we have picked something here and here. How to convert the decimal value to a fraction which we then use for getting our mole ratio. So let us try to see. In part B, we have been told that if the vapor density of the hydrocarbon is 29, what is its molecular formula? So we say that in getting the molecular formula, the empirical formula which we have got in this case, it is C2H5, we have to multiply by a simple factor n, and it will give us the molecular formula whose molecular mass is supposed to be given. But in this case, we have not been given the molecular mass, but the vapor density. So vapor density is supposed to be multiplied by 2 in order to give us the molecular mass. So let us use this one here. The vapor density we have multiplied by 2, and it is giving us the molecular mass. So let us try to work out the empirical mass. It will be n times the whole of 12 times 2. I've got the mass of carbon in this empirical formula. I'm adding it to hydrogen is 1, so it will be 1 times the number of atoms, which is 5. And the whole of this one should give us a total of 58. So let us work out the value of n. So 12 times 2 is 24 plus 5 is 29. So it will be 29n is equal to 58. And what is n? How do we get n? It will be 58 divided by 29, and our n is equal to 2. Please don't forget this step here. You know that if you are to get n, you are supposed to divide 58 by 29. Don't just say 29n is equal to 58, and therefore n is equal to 2. It will not be correct. Show your working clearly. And as we have done it here, we have shown our working clearly. Now let us try to substitute for the value of n in order to get for us the molecular formula. So directly the molecular formula of the hydrocarbon W is, let's substitute for n here. So n is in this case 2. So 2 times 2 gives us 4. So it will be C4. Then we come to this. 2 times 5 is 10. So it will be C4H10.